Hello everyone. My name is Ryoko Maeda, and I am the sales manager at Toray Research Center. First of all, I would like to thank you for this opportunity to speak with you here. Today, I will present the OLED analytical techniques TRC currently offers. Here is the agenda for today's presentation. Firstly, I will introduce TRC and our display analysis activities to give you some background into our company and share the value of our solution. Secondly, I will introduce our specific analysis related to OLED by sharing a case study using the latest analytical equipment and introducing the OLED analysis techniques we specialize in. Let me begin by sharing where the Toray Research Center fits within the Toray Group. As you can see, Toray is engaged in developing and manufacturing advanced materials. Its core businesses are organic synthetic chemistry, polymer chemistry, biotechnology, and nanotechnology. Toray was established in 1926 in Otsu City, Shiga, Japan, and began as a rayon spinning company. It has since grown into a global company with sales of 15,558 million euros, approximately 49,000 employees, and 310 affiliates in 29 countries and regions. This next slide shows the corporate outline of the Toray Research Center, TRC. TRC is one of the subsidiaries of Toray Industries. Established in 1978, it is now a world leader in analytical techniques for R&D and industrial fields. Since our foundation, we have developed more than 100 methods and installed state-of-the-art technologies, maintaining our experienced know-how. Our customers are not only within the Toray Group, but we also provide services to more than 12,000 requests from 4,000 private companies, universities, and national projects worldwide. One of our laboratories is in Munich, Germany. This slide shares our mission to contribute to society through advanced technology. TRC supports and partners with clients to help them deliver value that exceeds expectations. I would now like to share our portfolio of analytical methods. We have more than 100 methods. You can see some of them presented on this slide. When you have issues with your R&D or production processes, you can select the solution to solve your problems. In addition, not only do we have a variety of methods, but we have also been introducing the latest equipment since our establishment. Here are examples of the latest instrumentation we have installed in recent years. A world-first TM stem with an atomic-level resolution was introduced in 2022. Micro-RBS was introduced in Japan first, and nano-SIMS and GCIB TOF SIMS were introduced to companies first. This next slide shows our business areas. As you can see, TRC's focus is on a wide range of fields, and we are constantly updating our analytical technology to meet the needs of each field. While today's presentation is in the field of displays, it is important to know that our technology and services are not limited to displays but are also available in any field needing analysis. I will now start to focus on displays. TRC uses state-of-the-art analytical equipment and industry-leading evaluations to investigate, identify, and propose solutions to your problems. When it comes to displays, there are many different types, including OLEDs, LCDs, and automotive displays, and each has its unique issues. For example, in the case of OLEDs, luminance degradation and display defects are common. To identify the cause, TRC can propose and perform cross-sectional observation of the OLED layer and material analysis composition. Let's now look at a specific case study. TRC works with clients to understand the problem, formulate a hypothesis, prepare samples, analyze, and provide discussion. Here is a case study involving the analysis of the luminance degradation of an OLED panel. When faced with such a problem, TRC can help you understand why the problem occurred and how to solve it in the following ways. First, after asking about the nature and background of the problem, we perform a comparative measurement between the degraded product and the unaffected product and compare the results. In this case, we decided to analyze the PL measurement of an OLED layer with an advanced gradient process. As a result, we confirmed a reduction in the luminescence intensity of the ETL layer. This result led us to believe that the ETL component had degraded. A comprehensive report summarizes the analysis results. In this report, TRC meticulously identified each problem, conducted specific analyses, and recommended customized solutions. This next slide shows the history of analysis technology for OLED devices at TRC. To develop these technologies, especially for OLEDs, TRC has been developing analytical technologies since the early days of OLEDs. The left column shows the history of OLED, and the right column shows the history of TRC's technology development. For 25 years, we have established and offered new techniques every year. You can take advantage of these techniques in one inclusive environment. Today, for example, we can introduce you to the latest OLED analysis examples using plasma FIB and each of the methods shown in green. That concludes the first part of the presentation, and I will move to some examples of actual analysis. This slide shows the latest introduced device. The plasma FIB uses plasma ions of xenon, argon, oxygen, and nitrogen gas elements as the beam source for a focused ion beam, FIB, that enables precise cross-section fabrication. Compared to conventional gallium ion source equipment, the plasma FIB can process at a higher current, enabling cross-sectional fabrication over a wider area. We applied the state-of-the-art plasma FIB and SEM scanning electron microscope to the structural analysis of OLED displays. OLEDs are composed of layers of hard and soft films, such as organic layers, forming various structures, and there is a need to view a wide area without delamination. With conventional gallium FIB, the maximum width is several tens of millimeters, making it difficult to view a wide area from the edge of the panel to the pixel area. Using the newly introduced equipment, it is now possible to fabricate and observe a cross-section of a commercial product as thick as 1 mm from the edge of the panel without delamination. Here is a SEM image of the 1 mm wide section of the panel. The area A, the panel edge, and the area B, the pixel, are both observed in the same field. The following slide shows a magnified image of both. As you can see, at the area A, the panel edge, the edge of the encapsulated area is observed. In the area B, the pixel area, structures such as TFE and PLN of organic and inorganic materials are visible. These are visible together in one image. Do you need to observe the driving circuit part of an OLED display? The new equipment, which utilizes focused ion beam, FIB technology, allows precise control over the cross-section processing position with an impressive accuracy down to the tens of micrometers. This level of precision enables highly detailed and controlled material removal or modification. In other words, it can precisely process the cross-section at a specific position. It can also fabricate a wide range of precise cross-sections that are unachievable by polishing or broad ion beam fabrication, enabling accurate structural evaluation of a wide variety of devices. As one example, we introduced the 3D observation of the driving circuit part of an OLED display and the TFT part. 3D construction is achievable by repeating processing and observation to obtain a 3D observation image of the TFT part. After extracting digital slice images in the YZ and XY planes, we can observe the state of wiring, electrodes, contact structures, and semiconductor thin film layers. Moving forward, TRC can recommend high-contrast STEM for observing the stacked structure of OLEDs. This technique disassembles an OLED device and performs cross-sectional observation of the stacked layers. We have been developing and providing high-contrast TM since 2002. In recent years, we have improved the observation method and can now observe images with higher sensitivity with the high-contrast STEM. Upon magnifying the upper section of the central image, it becomes evident that the C layer is subdivided into 4 distinct layers, allowing for a more detailed composition evaluation than previously possible. This slide shows the cross-sectional structure. There is a demand to know the organic materials that make up the OLED layer, and TRC can respond to this request. The TOF SIMS with a gas cluster ion beam provides depth profiles that include chemical structure information of organic compounds, and it is possible to analyze components with concentrations of only a few percent and trace amounts of dopants and degraded substances. In addition, there is a need to determine the molecular structures of the host and dopants. TRC has identified these structures by GCIB etching followed by TOF SIMS MSMS. Other qualitative analytical methods available at TRC include LCMSMS with high mass resolution, NMR, LISA, and LDMS. These instruments can also determine the organic components' concentration and detailed structure. Recently, we received requests for quantitative analysis of compounds in OLED layers. As reference materials for OLED compounds in devices are scarce, TRC recommends using charged aerosol detector (CAD) analysis as an alternative for quantitative analysis. There are two types of detectors for quantitative analysis, UV-Vis and CAD. UV-Vis requires a reference material of the same compound to be quantified, while CAD allows semi-quantitative analysis without a reference material. With CAD, quantification is possible even without a reference material. On the next slide, you can see OLED films with a specific structure that includes both the host and dopant. Once prepared, CAD performed quantitative analysis. As a reference, the results were compared with the quantitative analysis by UV-Vis using a reference material. The quantitative results by CAD showed that the calibration curve for the host, CBP, provided quantitative values generally in agreement with the prepared values. CAD can be used for calculating dopant ratios and co-deposition ratios in commercial panels, especially when obtaining standard materials is challenging. In this presentation, I provided an overview of TRC and its OLED analytical techniques. If you need support with your R&D or production process, we can work with you to investigate and identify your problem and propose solutions. This concludes my presentation. Thank you for your attention. If you have any questions, please feel free to contact me. I will be happy to answer them.